Hello and welcome back to Calculus 1, section 4.6 on linear approximation and differentials. So now we are going to honor our ancestors and figure out the way they used to compute values. Well, actually, people were walking around with a book called log tables, and if you need a value for a sine, cosine, or ln or something, you would actually look it up in the book that only had tables of these values. And the way these tables of values were computed is what we are going to learn here. Now, clearly, today you just use your cell phone to use the calculator on it to figure these things out. But just go 50 years ago, you had to have the calculator handy so that you can compute, let's say, a square root of 10. Right, how much is square root of 10? So how would you compute something like this? Well, if you consider the function called square root, and that there is a value 10 somewhere, right, on that, what you know is that you can compute at 9. Because square root of 9 is 3. And if you draw a tangent line going through 9, you will notice that the y values at 10, at x equals 10, are close for square root of 10 and L of 10, and this is tangent line. So what is the hack? The hack is that instead of computing 10 in a square root, you'll be computing 10 in a tangent line. And that's just a linear calculation. That's a joke. You can do it with a stick in the sand. So let's do the problem. We are technically going to find the tangent line at 9, and once I have a tangent line, then I'm just going to compute 10 inside the tangent line, and that should be good to go. So what's my tangent line at x equals 9? Well, we start with our function, which is square root of x, and we find the derivative, which is 1 over 2 root x. And we know that we find the slope m when we plug in the value in the derivative, which is 1 over 2 times square root of 9, which is 1 over 6. So now that I have 1 over 6, I am going to calculate the y value. So y value is f of 9, which is square root of 9, which is 3. So now I have 9, 3, and 1 over 1, 6. So y equal mx plus b. Y is 3. M is 1 over 6. And this is 9. And then plus b. 9 and 6 cancel. We get a 2 and a 3. So b is equal to 3 minus 3 halves, which is 3 halves. And we get that our tangent line is y equals 1 over 6x plus 3 halves. So this is the tangent line, and we can now claim that the square root of 10, you can also call this L of x, right, if you write it in a function form. L stands for linearization, because the tangent line is a linear line. So we linearized the problem, and now square root of 10 is actually L of 10, which is 10 over 6 plus 3 halves. 10 over 6 cancels down to 5 thirds plus 3 halves, and that's a 6, 10 plus 9, 19 over 6. And that's approximately 3.6 6 into 1, I believe goes like this. 3.16666 forever. So what we computed is the square root of 10 is approximately 3.166 going on forever. You saw me not use calculator anywhere. We only used basic operations. We did not go anywhere close to the square root or any calculations that the square root requires, other than square root of 9 is 3. So now I can check this by comparing it to what the calculator is going to give me. And the square root of 10 in the calculator is 3.162. I am off on a third decimal, right? With something that I have not used calculator for at all. So we can compute values this way, and it's really cool. So your job is to find the tangent line, and when you find the tangent line, you compute your number in the tangent line. Let's do another example, and then we're going to write the procedure for tangent line in a single formula, which is really awesome. But before we do that, how much is ln of 3? Okay. What is the close value to 3 that works well with ln? ln of 4? Nope. Well, ln has to have some number in it. You have to compute it. So which value works well with ln to compute without a calculator? 0 will give you negative infinity. ln of 10 we can't compute without a calculator. ln of 1 is 0. Okay, that's the one. But is there something closer? ln of 2 can't be computed without a calculator. E. ln of e is 1. E is close to 3 because it's 2.7. So we're going to find the tangent line at x equals e, because e is about 2.7 close to 3. Your job is to find the closest possible value to the value you want to compute. So e is close to 3. So anything that has, more than 2, you want to compute ln of 2.7, right? Well, e is close. ln of 2.1, well, e is close, right? If you want ln of 1.5, then you use 1, because ln of 1 is 0. So there are many values that you can pick. Your job is to pick whatever value is closest to the number you have, and then use that to find the tangent line. So what do? We have our f of x function, which is ln x. We have the derivative, which is 1 over x. And then we have the slope, which is f prime computed at e, which is now going to be 1 over e. The y value is f computed at e, which is ln of e, which is 1. So now that gives us e comma 1 as a point. So what I do is I write y equal mx plus b. And if I have y equal mx plus b, I can plug in y, which is 1, m, which is 1 over e, x, which is e, plus b. These e's would cancel. 1 equals 1 plus b. b equals to 0. So the tangent line would be y equals x over e. You can also call it L of x equals x over e. So how much is ln 3? ln of 3. Well, it's approximated by L of 3. And that is simply 3 over E. So now we just need to compute that. And we can do this without a calculator because we are bosses over here, right? E is about 2.7. So this is going to be 30 over 27. When you cancel by 3, you get 10 over 9, which is approximately 1.1111 forever. So I just keep 2 ones and put the bar on top. So what we calculated here, that ln3 is approximately 1.11. Now, calculator, check. Ln of 3 approximately equals to, then you take your abacus, and you put ln of 3, and you get 1.0986. That's very close to what we have, because this 6 will make this into a 9, this 9 would make this into a 10 over here, so we are technically good. Yes?
Wait, I'm just confused. How did you get y equals x over e? Where did the x over e come from?
Okay, so let me write it. Let me write this. So it's gonna be slope 1 over e times x plus b, which is 0.
I thought we canceled out the e's though.
That's just in calculation for b. Has nothing to do with anything.
Oh, okay.
Now you have to keep your y and your x and just plug in m and b.
Okay.
So m is 1 over e, right? And we can just call that x over e plus 0. We don't have to write. So the linear line over here will just be x over e. And we plug in our number 3 for x. So instead of computing ln of 3, we compute L of 3, which is linearization, and we get the value. And it's, as you can see, very close. Now, can we use this particular tangent line to compute ln of 100? No. Very good. This works only around the value you picked to find tangent line, right? So what is your pick? Your pick was E. That means that, let's say anything from, I don't know, 2 to 4. Maybe anything from 2 to 4, you can use this tangent line. And then after 4, well, most likely they're not going to work well together. So we don't push it. We try to find other values. So now, how do we know? Well, if you have ln, you should always use some kind of a power of E as your choice for x to solve the tangent line. So if you care about these things, you can just make a little chart of important values for ln. Obviously 1 is the first one, and then e squared, e cubed. But then you want to know how much these are, and you can just keep plugging them into your calculator. So this one is about 2.7, and then you have e squared. So you punch that into the calculator, and you get about 7.4. And then e cubed. So e cubed is about 20, and so on. So now, if I want to calculate ln 10, well, I better use e squared, because e squared is closer than e cubed. Now, maybe we can use e to the 5 halves, right? E to the 5 halves might get closer to 10 than 7.4. I don't know. We can try, right? And see how much that would be. So e raised to the 5 halves is 2.5. We get 12.2. 12.2 is closer than 7.4. So yeah, we can use that. It just depends on how much you want to compute and what precision you actually need. Right, in engineering, people multiply everything by a safety factor of 1.5, not to worry about these things. But All right, so now we understand that we are using the tangent line to compute the value of the function, to approximate the value of the function. So now, what I want to do is I want to write a single formula for the tangent line, which we will call a linearization. So linearization L of x is equal to f of a plus f prime of a times x minus a. And put that on a cloud. So this over here is the tangent line written as a single equation. So all of the features which you used to do separate, and you still have to do them separately and then feed into one formula, now you have in one formula. And some of you might be recognizing this formula as y equals y1 plus mx minus x1. You have seen this formula in your algebra class. It was y minus, come on, y minus y1. That's the way you saw it. But you can move y1 and just have this. Cool? Yeah. So the tangent line is actually just your basic, what you used to call point slope formula, written in calculus terms. And now you can just crank that formula in one shot and get the tangent line. And then what do you want? You want the ln of 3, you plug in 3 for every x. You want ln of 10, you plug 10. So that's the linearization part, where you approximate the value, or let me actually write that here. So linearization approximates the value of the function. As opposed to differential, which is the second part of this, which will approximate the change. So now we talk about the second part, and then we can go for a break. Differentials. We'll start with a purple statement. Differentials approximate the change in function. So it's different. It is not computing the value, it's computing change. Now, can we compute the change exactly? Yes, but it's a lot of calculations, and then you have to subtract. And what do you do if you have the x cubed and the cube root of x, and all of these things that you might not want to compute without a calculator? Again, you have to think that most of this stuff was developed 200-300 years ago, and it was very useful because none of the stuff existed at that time. This was the only way. Today you have options of picking up your calculator and computing ln of 10. Even iPhone can do it. If you flip it on the side, right? Even the iPhone can compute ln of 10. So we can now talk about the change. The way to develop differential is to first write from pre-calculus y equals f of x, and then when you differentiate both sides, you get dy dx, and then f prime of x. So we are differentiating the notion that y is equal to f of x. And when we differentiate, we get the formula below. And now you ship dx to the other side, get f prime of x times dx. And the last upgrade is to learn about, in purple, change in x, which is denoted as delta x, is equal to x2 minus x1 when, I don't know, the ice cube is melting and the side of the ice cube went from being 1 inch long down to 0.9 inches long. Well, that's a 0.1 inch change in its length, right? So that's that. An important fact here is that delta x is equal to dx. So never mind, you can use either one of these. And that gives us the formula dy is equal to f prime of x delta x. And that's the one that goes on a cloud. We call this formula differential. Now you would say, well, is that dy the change in y? No. Dx and delta x are changes in x and they are the same. Dy, I have to write that in blood, is not the same as delta y. And delta y is y2 minus y1, which can also be f of x2 minus f of x1. So they are not the same, but they are close. Not the same, but these are close. And because they're close, that's why we say that differential approximates the change. Yes?
But dx is equal to the change in x, which is equal to x squared minus x1.
Mm-hmm.
Okay, but it's just not the same for both.
No. They're close, but they're not the same. So now, the true change in y is approximated by dy, which is f prime of x delta x. So this is what you are going to use in your calculation. So let's take a look at some, calculation to understand this. And I'm going to just take whatever basic problem we can here see, so we can just look through this. Yeah, whatever, we can pick whatever. So let's say y is equal to, or f of x is equal to whatever, 3x cubed minus 4x when x grows from 1 to 1.2. Okay, immediately you are assigning x1 and x2 states, because your first thing you have to calculate is delta x, which is x2 minus x1, which is 1.2 minus 1, which is 0.2. That's your first calculation, and now you have that delta x is equal to 0.2. Put that in a bank. The next job is to find the derivative, which is 9x squared minus 4. And now finally, we say the exact change in y is approximated by dy, which is the one that I can compute. That's the derivative times delta x. So now we just plug everything in. The derivative is 9 times, and your x is 1. You take initial value there. So all of that was the derivative, times delta x, which is 0.2. 9 minus 4 is 5. times 0.2. And how much is that? Very good. So we just approximated the change in y as x changes from 1 to 1.02, and that was 1. Now, since this was a joke of a problem, we can check. To find the exact change, we need y2 minus y1, which in our case is 9 and then x squared. No, we need 1 squared here, minus, no, that's not my function. Should have copied the function. F of x is equal to 3x cubed minus 4x. Much better. So, we discovered from the text when x grows from 1 to 1.2. So, x1 is 1, x2 is 1.2. And now when I start computing these things, I'm going to use just at 1. So I have 3 times 1 cubed minus 4 times 1 minus, and now we use, no, I was right. It was supposed to be 0.2 in these ones. 1.2 cubed minus 4 times 1.2. There we go. Minus 3 times 1 cubed minus and minus cubed plus 4 times 1. So now we compute this and we'll see the change in y. So 1.2 times 1.2 is 144. Well, I mean 1.44. And then times 1.2. It's going to be 3 decimal places. So that's 882. And then 144, and what do we get? 8271, and 3 decimal places. There we go. Oops. So we have 1.728. Nine plus 4, 13 minus 3, 10 minus, so 5.2, right? 5.2. Something is terribly wrong. Oh, I did 3 times 3 instead of 1.2 cubed. There we go. And then times 3. So this is 5.2. Over here, 5.2. That's the mistake. So now we have 5.2 minus 4.8 plus 1 to give me 1.4. There we go, much better. Whew! Scared me. Our calculation said that the change is 1. The calculation that was done through the functions, the way you find the difference, is 1.4. That's 40 cents off. We're still good to go. Now, what's most interesting about these problems for differentials? Well, they approximate the change, and with that, some very important engineering aspects come up. One of those is the fact that certain design depends on these calculations. I'll give you a few examples and we'll see what they have in terms of word problems. You draw over a bridge, right? Large bridge. And it has this. Why does it have this? The break in a road. Yes?
So depending on the weather, if the weather increases, then it
expands, yes. As the things get hot, they expand, right? So you have, let's say, in this case, bridge. You have these breaks in the bridge length, and they're like that on the road. Over the summer, those gaps close because the bridge expands, and in the winter, the bridge shrinks, and those gaps are more open, right? So now you think of a bridge, and you think of a bridge as something that it's long, right? And in terms of like length versus the width, right? So you can regard the bridge as one-dimensional, even you know it's a three-dimensional object, but you can just regard it in terms of its length. Generally, they say, oh, yeah, that's a long bridge. No one says, oh, it's a really wide bridge, right? No one cares. So that's that one. Another one would be trains. When you go on a train, the famous sound, tick 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 tick, tick 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 tick, tick 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 tick. Why? What's that sound? Right? Where is it coming from? Is it a broken train? Because every train you are ever on always has that sound. And all of a sudden, that sound is very faint in the summer and really annoying and loud in the winter. Where's that sound coming from? Anyone? Yes? Tick tock, tick tock, tick tock, tick tock, tick tock, tick tock.
Little gaps in the rails.
Yes, the gaps in rails. Rails are very long. And the only way they're going to expand in a heat is lengthwise. So if you are laying the rails on those wooden planks for trains, and you lay them next to each other without a gap, right? When they try to expand, they're just going to pop out. You can Google the pictures of improperly placed rails. They pop off. They're all curled up like curly fries. This is how bad it happens, how bad it gets, actually. So the length of the rail, and then there's a gap, and then another rail, then another rail, and a gap, and another rail, and then you have those, right, going like that. So there is a gap there, and since all the trains have two sets of wheels, right, you have two sets of wheels in front and two sets of wheels in the back of every cart, right? When the first wheel goes over the gap, it gives you a tuck, and then the second wheel gives another tuck, 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 and then it hits the next rail, tuck, 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 and the next rail, right? So that's where the sound comes from. And again, design-wise, very important to have it. So about 2 decades ago, music used to be stored on something that's called a CD, compact disc. It looks the same as a Blu-ray disc today, right? I know that you pretty much are not familiar with those things anymore. So these discs have data written on them. You put this disc into a CD player, which is something that you might have in a car, I don't know. And that disc spins very, very fast. Now, there is, underneath the disc, there is a linear rail with a laser that would hit the disc with the laser beam. The laser would bounce off, and it would read the digital information stored on the disc. And that's it. You send that information into a decoder. Decoder converts that signal into electrical signals that are sent to speakers, and you have the music. Oh, cool. Yes.
I used to burn CDs from like YouTube converters, but then it's like, how does that work? How does it go from YouTube? Like I used to do it all the time. It's like, how does it go from YouTube to the CD?
Well, it's a whole bunch of software, right? And it has the laser, but the laser is the key over here. Why we're talking about it? What happens to objects as you hit them with the laser? They? Well, depends on the strength of the laser, but what always happens? They? Yeah, but that's not what I'm looking for. You're correct. I'm looking for something else. What happens when you hit something with the laser? It? No, that's the same thing he mentioned, and I already mentioned that. What happens when you hit something with the laser? That we would care about in this case. Yeah, but what causes that? Guys, when you hit something with the laser, what happens? I'm not talking about Star Wars here. I'm talking about lasers that we have. It heats up.
I said it burns.
Well, burns means there's fire. There's no fire here.
Like
So when you hit something with a laser, it heats up. When it heats up, it expands. And now the disk is slightly larger. And that happens over time. So the longer you play, the hotter the disk, the more it expands. So you have to read the temperature and correct for the change in the size of the disk, radius of the disk, because the laser is very precise. And if the laser is not reading the proper location where the data is, well, you don't listen to CDs, so you would not, right? That's what happens. It can't read the information, starts skipping. So the software has to, hardware has to measure the temperature, software has to do the calculation, and then either slow down or speed up the movement of the linear rail that has a head on it, right, the laser head. So it moves. The disk stores information here first, and it spirals out. So your first song is always going to be there, and the next one is, and the next one, the next one, the next one, right? So layers going outward, and you would see that even if you, there's so many of these things that, me growing up and listening to CDs, I knew exactly what I had to be very careful of. You never scratch the disc on the top, right? Because that immediately destroys the disc. The bottom scratches are not as bad. You can buff them. That's not a big deal. The scratch on the bottom, but the people usually say they take the disc in the good old days and they put it upside down on a rough surface so they don't scratch the bottom. And I'm like, no. Scratch bottom, you can buff. If you scratch the top, you scratch the layer which contains information, because the film with the metal, right, that contains the data is actually right under the picture on the top of the disk. And the bottom is just a layer of see-through plastic. So if you have scratches on the bottom, you can buff it, right? And it's gonna work. Scratch the top, you ruin the data, and you're done. Like some people etch in their initials on top of the disk with a ball peen pen. It's like, well, now you can throw it in the garbage. You can only use Sharpie on it, right? So these are the things that don't know about. So it was a lot of headache. Plus, you put it upside down in the sun.
That's like literally all I do with CDs, just put it upside down. So, like all my DVDs too.
We used to have a giant book of sleeves of
Yeah.
DVDs.
Yeah.
My mom's manager illegally downloaded the whole Harry Potter thing for us. Like that.
What is the name and the number for the stream?
I don't know. Now he's Foot Locker, but it's Backstreet Boys and Britney.
So So now you see this in the design, right? So now it goes for DVDs, it goes for Blu-ray, right? Any of these devices that would read using the laser inside, they all work on the same principle, just, more data and more data and more data. Used to be 700 megs, and then they moved to a DVD, which was, I think, 4.5 gig, moved to 20-something gig for Blu-ray, and so on. 25 gig, I don't know what it was.
If you convert like a VHS tape onto CD, is the quality better or is it like
No,
the same?
you cannot improve the quality without
But
remaster.
Is it the same quality or is it worse?
Depends on the aspect ratio. I'll tell you after the class, but it's the same or worse. You can't make it better. That's the key.
But if
Can't you use recorders and stuff like that?
You can only if you use some enhancing software or filter to remaster it, right? To clean up and put in frames and stuff like that. We'll talk about it afterwards. So let's finish this first. All right, so let's take a look at one of these word problems to make sense out of this, and then we're done. So let's see what they have. Approximate the change, blah, 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 blah. Okay, so let's see. Approximate the change in atmospheric pressure, for instance. Usually I work on this one because it has exponential function. And I can mention another one. Oh, another important one, guys. Tire pressure is another one. Because you see a lot of shredded tires on a highway in the summer and not so many shredded tires in the winter. If you're not paying attention to the tire pressure, it can end you, actually. Imagine your tire exploding, like one of the two front tires exploding while you're driving 80 on a highway. That's not usually going to happen to you.
What? I had a question.
So, yeah, okay. So, PV equals nRT. nR, this is constant, so we don't care. P is the pressure, V is the volume, and T is the temperature. And this is for ideal gas. Ideal gas. The gas in your tire is not ideal, but still this formula applies. So if you think about this, there is a huge difference in temperature when you're driving in 40-degree weather and you're driving at 105-degree weather, right, in the summer. And to both of those temperatures, you get to add the temperature that it's there due to friction of the road to a tire. You want your rubber, right, the tire, to have as much friction with the road because that keeps you from sliding off the road, right, and it keeps you moving forward. If you take a regular tire, you put it on ice, and you spin the car, it's not going to go anywhere, right, because there is no friction between a tire and a road, and it can't move you forward. So the more friction between tire and a road, the better, but the friction causes heat. Now, in the summer, you add more heat because, again, the temperature in the summer might be 60, 65 degrees more than that it's right now outside or this morning. So clearly, when the temperature goes up, that means that the right-hand side value went up, so the left-hand side has to go up. But the tire is of the finite size, right? So this V has to stay constant because it's not a balloon that you can inflate more. It has actually metal rings inside, right, to reinforce the tire and so on. So it's not something that you can just inflate as far as you want. So when the tire is inflated all the way up and the pressure in it, right, the pressure is the one that you get to control, how much air you put inside. So with more temperature on the right, the pressure on its own will go up to keep the volume of the tire steady. Well, if you didn't lower the pressure and now it's summer, right, then the extra temperature there will make the pressure go up, and that makes the tire explode, right? So that's why you want to make sure that every time in the summer your tire pressure is less, and every winter you can go almost up to the maximum. Every tire lists the maximum tire pressure, generally anywhere from 35 to 50 psi. So most of the people keep it like 36 and so on. You can put 40, 45 pressure in the winter if your tire goes up to 50, let's say. But in the summer, 32s or something like that, and you don't have to risk this, tires exploding. You have to take care of these things.
The number they put there, the 35, right? Don't they account for the temperature changes and stuff? Or do they just put 90?
They put 35 because 35 is, it's not a max. If some people say the rating on the tire is 50, put 50. Right? Because you put maximum rating, you never put maximum rating pressure tire in the summer. And you can calculate these things as a change. Yes?
So how come in the winter time, like in the morning when I get in my car, my tire pressure light comes on, but in the summertime it doesn't come on?
Because it's the higher pressure.
But so like my tire pressure light won't come on when my tire pressure is too high, but it will come on when my tire pressure is too low?
Yes. Because that is indicator to the car that your tires have low pressure, so maybe you have a flat tire. The only time when the pressure thing comes up in a car is when the tire pressure is too low, because car thinks that you have a flat tire.
Yeah, but it would be helpful to also know when my tire pressure is too high and my tire.
Yeah, but that also would increase the cost of the car, so no one makes that.
Does Elon Musk make it?
No.
Oh, okay.
Sorry for disappointment, but so you will have to actually manually worry about that stuff. All right, let's take a look at this problem. Change in atmospheric pressure. Change in atmospheric pressure. So change in atmospheric pressure when the altitude increases. So altitude increases. Altitude increases from z equals 2 kilometers to 2.01 kilometers. That's 10 meters difference, which is about 5 times my height. And the pressure formula for atmospheric pressure in terms of the height is 1000 e to the negative z over 10 as the exponent. Awesome. So change in atmospheric pressure is approximated with the dP. My x and y variables for the variables that are given in this problem, right, to me, in this problem. So this is usually x, so now we call that z, so my delta z there, and this is usually f of x, which is y. Well, now I instead of f of x, I have p of z, right? So I'm just swapping this for the variables that are in this problem. Now, delta z is new minus old, so 2.01 minus 2, which is 0.01 kilometers. So now I have delta z, and now I need the derivative, and that is going to be 1000 e to the negative z over 10 times negative 1 over 10. So this works out to be negative 100 e to the negative z over 10. I said 100. There we go. Because 1000 divided by 10, right, is 100. And now I have the formula. So dP is equal to negative 100 e to the negative 2 divided by 10. This is why you were supposed to cross your z's, because in this problem, z equals 2. If you write both of them the same way, you don't know which one is your z and which one is your 2. Cross your z's. so you don't get in trouble. And you'll need that for your Calc 3, X, Y, Z. P, and then times the change in Y delta Z. So now these two would actually cancel. And all I have to compute is, oops, there's a negative in front, how much is e to the negative 1 over 5. So we have e raised to negative 0.2, and we come up with delta p is approximated by dp, and dp turned out to be negative 0.82. 0.82, and atmosphere, ATM.
If you wanted to make this like spicy, right? And could you use the tangent line thing that we just learned to approximate the value of negative 2 to the negative 1/5?
Yes, nice. Because that, yeah, just 50 years ago they would have to do that, right? Right now, guys, you always live at the best possible time. That's the way it is, you know. Like 99.999% of population just, 100 years ago lived in near poverty at like $1 a day. The whole planet, right? And that 0.001% of the people were the ones who were the lords and had the money, right? It's just amazing. Always amazing times. Cool. Now, why is this negative? Well, what do we know? What happens with atmospheric pressure as you go up? There's less atmosphere. So there's less atmospheric pressure, right? Which is why Iron Man can't fly. Falls down. Yeah. Look it up.
Why what? Why what can't fly?
Iron Man. His suit freezes and there's no air.
That's
yeah.
like after a while.
Yes, after a while. Mm-hmm. Kilometers? Kilometers are comparable to miles. Yeah. You got it. Well, that's the new technology, but I'm talking about Iron Man 2. Iron Man 2. And Iron Man 1, too.
You're saying someone knew that and accounted for that in that movie.
Of course. They actually do check these things. That's it, guys. That's differentials. Bye.